Cornell. He did his PhD at UW, and he does a lot of very cool stuff at the intersection of hardware and software. And I will say no more.
Thanks, Matt. I was thinking about this about FCRC and about like the different areas within computer science. I don't know. I feel like in CS we're like a little over obsessed with like defining things as your affiliation with a certain area. So we think about this a little bit too much. But I was thinking about it, and I was thinking about like that. It occurs to me that the areas within computer science, everyone has a credible claim to make that their area is like the fundamental question in computer science. Yeah? I think this is totally cool. Like, it's like completely allowed that everybody have like their version of like why the thing that they are doing is the most important problem. It like is computer science. So, for example, you might say that like the HCI people, for example, are asking the question like, how do we harness the power of computing? Like we got computers, but like how do we actually make them do things? You know, that's kind of fundamental. That's like in some ways, if you think about it, that's the question of computer science. It's like how do you take this vast potential we know exists and like put it to use for the humans actually want out of computers. Machine learning, for example, get to ask the very tantalizing question, what are the secrets of human intelligence? I'm a little bit jealous of that question, I guess. But I was thinking about the two areas that I'm involved in, which are programming languages and architecture, and I think they ask really related questions. I actually think there's two different, like, sort of fundamental computer sciencey questions that I think programming languages people ask. The first is just like how do we get computers to do what we want them to do? That is, like, how do we even like make computers do stuff? I think that's pretty fundamental, right? Like if we didn't have programming languages, we couldn't like actually accomplish anything at all with computers. But I think there's another question that motivates me and other programming languages people when they think about like their relationship with computer science, which is asking the question, what is computation really? That is like this is the thing that initially attracted me to programming languages, is the idea that we can remove all the layers of like uncertainty and really get to the heart by like formalizing everything, by like getting rid of all the hand waviness and all the guessing, and like really answer questions. Like it's this sort of these formal tools that like make programming languages exciting to me. So I think this is a good way to like make the case to your friends and family that programming languages is like the fundamental question of computer science. But I think that like architecture is an example of a field that gets sort of short shrift for like, I don't know, it's you're just like building machines or whatever. Like how important could that really be? But like, of course, when you think about it, architecture is asking an equally fundamental question, which is like, what even is a computer? Like how do we like build these how do we like take raw sand and turn it into something that can actually do computation? So I work at the intersection of these two things. Here's an intersection. And I think in my message to you today, I'm going to talk about in a particular project we're working on stuff, but my main message here is that this intersection is interesting. That is like the intersection between asking what computation even is and like what makes a computer a computer. There's a lot of cool stuff going on at this intersection. So in order to do this, because we're at PLMW, I have to like go way back to the very beginning of computer architecture, of course. So we have to talk about Moore's law. So this is the actual thing that Gordon Moore wrote in 1965, which is kind of kind of garbled, I guess, by time and turned into like this fact that you've doubtless heard being stated about like this is the law that has governed computer hardware for decades. And of course, the implication is not just that we get that transistors are getting smaller. That wouldn't be very exciting, but they get cheaper and also they get lower power, and that's what turns computers. That's what has like the engine of progress that has driven computers forever. I thought it was like it's actually super interesting, like how literal this was in the original paper. This is an actual graph that I got from back there, and it sort of looks like this. Like it's important to note that the y-axis here is exponential. So like this thing that looks like a line is in fact an exponential curve. Anyway, so like this is the projection of that thing off into the future. So if you take that exponential curve, it followed that same thing from the 60s. That followed that same trend for a shockingly long time, and then of course it did this very dramatic thing where it stopped doing that, which is very scary to all the computer architects. And I'm telling you this story because I think it's important to to understand why computer architects are so freaked out right now, and why that there are problems to solve at this intersection. So I want to sort of do a little revisionist history here and think about the trends that have been influencing computer architecture. And I think the way that people think about it now is that for a really long time, when we were riding this exponential curve of computers getting better, without the intervention of computer architects, that is with just the device people, the people who manufacture individual transistors getting better and better at their jobs, computer architecture didn't have that much of an interesting job to do. That is we were sort of in this free lunch era. And we, around the 2005 mark, we crossed over, and it seemed at the time that the thing was going to be that processors themselves were not really getting all that much better. Individual processors won't get better. So I remember at this time, 2005 is when I started college, and at this time I remember that when everyone told this story, the thing they were saying is that the next thing, the next exponential curve that we're going to ride, is entering the multi-core era. That is instead of building individual processors, we're going to build these massively parallel machines, and we're going to enter this new exponential curve where soon we're going to have tens of thousands of cores on every processor. And there were a lot of slides made that looked like this, and the things that looked like this. I saw a lot of these slides at the time. And of course, the results turned out that now all our laptops have 100 million cores as a result of this exponential trend. In fact, of course, here's the actual results as time goes along the x-axis, and the number of cores that result. It's pretty uncommon to buy a computer with more than 16 cores. You can find them, but we didn't enter that exponential trend. It just turned out that this was for various reasons that I'm not going to get into that have to do with the manufacturing technology all the way up to the application. This did not turn out to be the reality. So the multi-core era came, and it also went. And now we are in a much weirder era that does not have a name. Or maybe it does. It was named, perhaps, by these guys. Do you recognize these guys? These are last year's, the boring old Turing Award winners from last year, instead of the exciting new Turing Award winners from this year. So I'm summarizing a little bit here of what they said in their Turing lecture. The reason this picture is all blurry and crappy is because I actually took it. I was sitting in the second row watching this talk. So what Hennessy and Patterson said is that they sort of told the story of the performance returns from Moore's law are over, and so the message that they were trying to get across, I think, in the talk was that the only thing we can possibly do is to trade off the generality of the machines that we're building. That is, instead of building these CPUs that can do everything okay, instead we need to build lots of individual kinds of machines, that is, specialized architectures that can do one thing particularly well. And we have to somehow make do with that crazy world where machines are not individual things, but they're giant, complex intersections of massively heterogeneous kinds of hardware. So the era that you might call this is that we're now in a new golden age of computer architecture. Because it sounds kind of bad, a world where we can't make advances the same way that we used to. But I think the point of this Turing lecture was to sort of do some marketing jujitsu and take that thing that seemed really worrisome and turn it into something that sounds like an opportunity. That is now we have all these cool problems, and finally our jobs as computer architects can be interesting again. Okay, so this is my pitch for why computer architecture, in addition to asking a fundamental question about what computers even are, is now more relevant than ever because we're in this new golden age of computer architecture. So I want to talk about this notion that we're going to be building machines with really specialized processors that can do one thing extremely well. And I'm going to talk about a high-profile success that came out of Microsoft. This here is Doug Berger, who's now at Microsoft, previously was at UT, and what he's holding here is a card called Catapult, which has a kind of reconfigurable hardware on it called an FPGA. And this is what they did with Catapult was a gigantic success that took a specialized architecture, originally just meant that they configured to be just for doing a certain part of the Bing search pipeline. And the headline result that they got is that they could run the entire Bing search engine on half as many machines as they used to by augmenting it with this specialized hardware. So this is a splashy and fantastic result out of that comes out of the golden age of computer architecture. So this was very, very cool, and I strongly recommend this paper reconfigurable fabric for accelerating large-scale data center services that describes what went on here. And this was like a huge result, and everyone was very excited about it. Another thing that is huge about this paper is the author list. You will notice that it has 23 authors. And the reason is that this is extremely hard work. That is like for just a single application, the brain trust at Microsoft has to pour a tremendous amount of effort into producing specialized architectures, even for these reconfigurable architectures, to get them to do what you want. So the reason is that the tools and the programming languages, this is now we're crossing over from facts. I was just telling you facts. Now we're moving over into opinion. The reason I think that this is so hard is because of a programming languages problem. That is, I think that we need to rethink the way that we design hardware from a programming languages perspective instead of a computer architect's perspective. So let me tell you a little bit about what people like these people do when they're designing customized architectures, accelerators for data centers, for example. They run something called RTL, which is the register transfer level abstraction. So if you ever heard of Verilog or VHDL or BlueSpec or Chisel, these are all RTL languages. And they're all, and they were originally meant for designing things for designing, for example, processors, things you're actually going to tape out and get real silicon from. And they've been repurposed for targeting the reconfigurable architectures, namely FPGAs that are, for example, involved in Catapult. The problem with programming in RTL is that it is an extremely low level of abstraction. That is, like, this is an analogy that I think is perhaps outlasted its welcome, but like I think it's still sort of useful that that RTL programming is roughly like programming by hand if you did everything by hand in assembly when you were programming a CPU. That is like the reason this is so hard is because the reason there's like so many people on that paper is because they are writing everything in the equivalent of just writing assembly by hand, not in a higher level language. There are higher level languages, but they're not seen as being like the real language you want to use to get real efficiency out of this hardware. So like, I think it's a really interesting question to ask, like, what would a good, even like slightly higher level language look like? That is like a slightly higher level language, like C, for example, compiling down to assembly, like something actually meant for humans to write, that doesn't like hide the important details of what makes the underlying hardware tick. So I wonder if you have any ideas about like what that analog would be. That is like in the architecture world, what do people think of, like what have people invented already as the higher level language that compiles down to RTL? What do you think? HLS? The answer is basically C. That is like, for some reason, people have decided that the thing to do, the higher level language to abstract this like completely different programming model is to like take C programs and compile them down to RTL, which is crazy, but it has a name. It's an entire field. It's called high level synthesis. The idea of like compiling from C programs all the way down to this thing, which is essentially like a description of a circuit, is a big area, and I think that there is one big problem with it, which is that it's impossible. That is, like, it is really a complete mismatch in the semantics of our languages. So it turns out that like when you're these tools, which actually exist, they're actually compiling like a weird, funky, awkward subset of C, sometimes very slowly to Verilog. It's not they don't actually compile C. They compile it sometimes a little bit. I want to pick on this particular sentence that I found in a paper about HLS that I think is like so fascinating. I'm going to read it out loud. It says that since RTL programming in VHDL or Verilog is unacceptable to most application software developers, it is essential to provide a highly automated compilation synthesis flow from C or C++ to FPGAs. And the reason I'm picking on this is because I agree with half of this sentence, but like so much not with the other one. I think there's like no particular reason why people would want C or C++ to be the abstraction for this thing. So if I were to summarize what HLS does now, what high-level synthesis is now, is that it is like an enormous series of ad hoc checks followed by a broken compiler that sometimes emits Verilog. So the project I want to pitch to you that we're in the middle, there's no publications on this yet. We're still like, this is a surprisingly hard problem that we're still working on. Is the design a programming language based on a type system that can certify to you that if your program type checks, then it does literally generate hardware that doesn't surprise you. And that's our language has lots of names because we can't agree on a good name, but one of the names is C#. So I want to tell you a little bit about what it looks like to program in HLS. So here's like a really simple C program that just loops over a couple of arrays and takes things out of the first array, does a simple multiplication, and then puts the result into the second array. This is like the sort of thing that you would hope it should be able to map to hardware. In fact, like here's the circuit, the kind of the configuration for an FPGA that you might generate. You've got like an actual circuit that implements multiplication connected to a memory that holds the first array and connected to another memory that holds the second array. And of course, this isn't like super great hardware. Like the whole point of generating hardware is you should be able to make things go really fast. So like a very standard thing you might want to do is stamp out multiple copies of that circuit. That is like not just have like one multiply circuit, but 5 of those, which sounds good. And in HLS, here's what you do, #pragma. You put this inside, you put a special annotation inside your loop to say I would like to unroll this. That is like copy and paste the body of the loop multiple times. But the thing is, this actually doesn't work. This compiles as something totally surprising that like sometimes that adds a whole bunch of extra logic because it's violating a constraint that exists in the actual hardware. The point is that that memories being physical things, you can't read 5 things out of at once. That is, like, you can't have 5 multipliers feeding their data out of a single memory all at once. So instead, you have to do this other thing. That is, you have to put additional annotations on to say, I want to break that memory up into smaller memories that I can access in parallel. And now you get this hardware. But the point is that what's going on in these programming languages that are C with a bunch of pragma annotations, is there's a bunch of hidden constraints between your program, the way you access things, the way you declare variables, that aren't exposed to you as the programmer, but you need to be carefully follow in order to get predictable hardware. What we build instead in C# is the idea that we can use a type system to enforce those constraints. So rather than being sort of latent and like enforced by compiler crashes, now we can describe them with a type system and inference rules. So the idea is based on substructural logic and substructural types that where the essence of the problem is that things can be used up. That is, we want to get a type error here that says that when you access a memory, that means it's used up for this time step, and you can't use it again. So this is an old idea. Substructural type systems are an old idea in programming languages that are coming into their own. They're, for example, the underlying technology behind Rust, and we're repurposing them to track the resources that go into hardware generation. I'm pausing because I want to skip over a couple of details here. So that's the essence of the type system we want to design, is something that lets you that like can track the consumption of things and therefore enforce the constraints that are left latent in a normal HLS program. So this is my preferred analogy. That is, like, I think that we need something that is not C, that is like a sort of a cousin to C, that is like something that literally describes what's going on in the hardware, but is nonetheless programmable for actual humans. And that is the role that we hope that C# will occupy. Here is our GitHub page. Despite this not being finished, you can actually clone the code. It's pretty crazy. The documentation is a quarter baked. But if you're curious, please check it out. It would be fun to have people play around with it. The higher level point, though, that I want to make in this context is that there's surprisingly interesting problems that nobody else is working on in this intersection between programming languages and architecture. And even more broadly than that, I think that programming languages is an intersecty field that intersects with lots of other parts of computer science that creates lots of really interesting problems. Those problems tend to be super, super hard. They're really difficult. But on the other hand, you don't have any competition. They're too hard for people to really get involved in. So, like, I don't know anybody else using affine types to try to describe hardware generation. There's like, a lot of people trying to make like, compilers a little bit faster or type systems a little bit safer for traditional architectures. But I think there's really interesting stuff to be done that you can leave everybody else in the dust if you stick with intersections between programming languages and other parts of computer science. Thanks, everybody. Yo.
Do you expect C# to be used by software programmers, or write it so that it can be used?
Yeah, so this is a very, your question was, do you expect C# to be used by software programmers? This is a very difficult and weighty question. Like, who exactly are we targeting? Are we targeting people who are like hardware experts, and they just want a more convenient way to do things? or are we targeting like software people who want to learn about hardware? It's the latter. That's what I care about. That is like the hardware programmers of the world. They're getting by just fine with a combination of RTL and like forcing HLS to do what they want. That's okay. They can keep doing that. What we're interested in doing is designing a programming language that is actually intelligible to like reasonable programmers who don't know anything about hardware. And we hope that like through this type system, we can actually explain what's going on in the hardware. That having a clean abstraction is I think what you need to introduce people rather than this like abstraction cliff you go off of when you switch from software programming to Verilog. Clean.
How are you going to bring some of the hardware constraints into account? Like this, besides the abstraction?
So what do you mean by some of the hardware constraints? Can you elaborate?
Like here, you have only 5 multipliers.
Yeah.
You know, you need to bake that kind of stuff into the program.
Indeed. Yes. So the way this works in C# is that when you bank an array into 5 different arrays, the type system sees that as 5 different affine resources that can be consumed. So like whenever you access things, you're actually accessing like one piece of the memory, one bank of the memory, and then that goes away and you can't access it again. But as long as you're well behaved and you access like 5 memories with 5 pieces of hardware, then we can certify that your program is valid and we don't need to add a bunch of delays into when we generate the circuit. Yeah.
I guess, do you have any hardware constraints that you are having difficulty sort of seeing how to fit them into a type system?
Yeah, pipelining. It's a very easy question. We're struggling a lot with pipelining. So a really important hardware optimization, then you have like a single piece of hardware, you can like feed in some inputs and it can march down a pipeline for a while. It can feed in some other inputs, it can keep on going. You can process 2 things at once with only a single piece of hardware. Super important as an area optimization. It is very hard to express at higher levels because like if you imagine this piece of hardware, you need to sort of like certify that like different times within the same hardware don't conflict with like other times. Anyway, it's a super nasty problem that we don't exactly know what to do about it yet. Yeah.
What about branch connections? I think that makes confusion. Can C# express that easily?
C# is not a language for designing processors. It's a language for designing specialized hardware accelerators for individual algorithms. So we're not interested in designing, in the features of high-performance CPUs. Yeah.
So if C shell is equivalent of C for assembly, just for the idea, why not stop there and go to Python level? That the programmer wouldn't care about the levels of the hardware design.
Great question. So your question is like, why stop at the analog of C and why not go like much higher level? I actually think I would like to broaden this question out a little bit, which is why to work on low-level programming languages at all? Like, for example, like why work on memory models for C, for example? Like you can just have like on clean semantics for memory models for C, because like experts are going to do that, and like might as well just work on like very high-level languages that use libraries written in low-level languages like C that those libraries can be written by wizards that for some reason are able to figure out like how the hardware works. I don't like that argument in general, I guess. Like I really think that in order to build good high-level abstractions, those need to be built on a tower of something. There's like something needs to exist below that before we can have like reasonable abstraction levels that get even higher. That is like I think that one responsibility we have in the subset of PL that focuses on systems is to really be solid about what we actually mean at a very low level so that we can build those higher level, or that people, perhaps other people, can build higher level abstractions on top of that. So the answer to direct answer to your question is that I think higher level abstractions are also important, but they can't possibly work if we don't know what we're doing at the lower level. Yeah.
So you mentioned that the type system will give you some guarantees about your program if it compiles. And I think you mentioned specifically like, oh, we'll talk about the memory performance and like the affine resources. Can you just talk a little bit more about what kind of guarantees it gives you and what you guys have already implemented and what you guys want to implement in the future for guarantees?
Totally. Yeah. So the main guarantee that you get is that a physical thing on the hardware design that you make, be it a memory or be it a circuit, isn't used twice at the same time. That's the thing that our affine type system enforces. So like you can't like have a multiplier somewhere that you're feeding two different sets of inputs to in the same cycle. That's super important to like having the thing be realized. The way that like traditional HLS compilers work around this currently is that if you do that, if you write a program that seems to do that, it adds a bunch of additional hardware in and a bunch of additional delays in order to avoid actually doing that. So the way our compiler works is instead just to prevent you from doing that in the first place. That's my summary. Yeah. Do I have time for more questions?
Got time for one more question.
Okay, go for it.
So if your type system would rule out a program that cannot be compiled to your program.
Yeah.
But does it also rule out the notion of that there's no equivalent program in C shell that somebody could transform this program to another equivalent program that could compile?
Oh, great. It doesn't tell you anything about that. That's a very good point. That is like our type system, as we formalize it, just classifies programs as to correct or incorrect. But I think it's like the writing is on the wall. The next thing to do is like once we have a formal description of what makes a program correct, is to be able to infer those things. That is to take a specification that doesn't completely tell you exactly how many multipliers and exactly how many banks, and be able to infer the answer when possible. That is like to take something that doesn't directly describe that and to like find an equivalent C shell program that we can certify as being hardware realizable. Yeah.
All right, thank you again.
Thanks everybody.